In this video, I will try to derive the isolated version of a buck converter using essentially a trial and error approach. Now, I have no clue if this is how the whoever invented the forward converter actually derived it from the buck converter, but learning it this way, this trial and error method that I'm going to show, gives a very good intuitive understanding of what is the role of each of the components that we're going to see in this isolated version, and also gives you a good understanding of the basic operating principles. Now, one of the reasons why power electronics can be so exciting is that there are so many possibilities, so many new topologies, control methods, and it is such a joy to always be thinking of coming up with your own new topology or a control method. And when you try to come up with something new on your own, you would most likely be following your trial and error approach, something very similar to what you're going to see in this video. In the previous video, we actually established the need for transformer isolation in a buck converter that essentially has a very large voltage conversion ratio. So we looked at the three main disadvantages, and that will form the basis for what we should be trying to do in an isolated converter in order to eliminate those disadvantages. So we consider this example of a 200 volts input to a 2 volts output buck converter with a load current of 10 amperes and the power 20 watts and 200 kilohertz switching frequency. The first disadvantage is the total VA rating, which is the product of the peak current and the peak voltage of the switch, the MOSFET. And for a buck, the voltage rating is 200 input voltage 200 volts, load current 10 amperes. That comes out to be 2000 VA just for a 20 watts converter. So that's extremely large. The second disadvantage was the switching losses, which for the same reason that the switch supports the entire input voltage as well as the load current. During the switching transitions, the current is at its peak value, 10 amperes. The voltage is also at the peak value during those transitions, at the start of the transitions. So that results in a total switching loss of 20 watts, which is exactly equal to the output power, entire output power itself. So the efficiency just by this loss alone is going to be less than 50%. So that is not acceptable. And the third disadvantage of just using a basic buck converter for a large step-down conversion application is the required L would be very large, because that is the expression for that has a 1 minus D, and D would be in this example 2 over 200 or 0.01. So that means this 1 minus D is very close to 1, and you require very large inductance. So those are the three major disadvantages of a non-isolated solution for this application requiring large step-down conversion ratio. And I promise that the isolated version will be able to solve each and every single of these disadvantages. Now, this is the buck converter of our specifications, 200 volts to 2 volts. Here, if you look at the switching voltage that I apply to the input of the LC filter, the voltage V1 essentially across the diode, this would be 200 volts when the switch is on and 0 when the switch is off and the diode is conducting. Okay. So even this on interval, this is really is not drawn to scale because D is extremely small and this interval is really short. But I've drawn it slightly bigger in order to see it clearly. Okay. And the average of this waveform is the 2 volts, that is the required output voltage. Now the main point of introducing the transformer isolation is to see if we can somehow make this waveform that switches between 200 and 0, can you, through the use of a very large step down ratio of the transformer, get a waveform which is something like this. Okay. So in this example, it is switching between a much lower voltage, N times Vn, and N is the transformer turns ratio, which for example could be as low as 1 over 50. So it's a 50 to 1. 50 on the primary side to 1 on the secondary side, 50 to 1 turns ratio. So what have we achieved? Here we saw that the D is 0.01. Okay. That's because it's switching between 200 and 0. And the D is 2 over 200. Whereas here this magnitude is 200 over 50, that is 4 volts. Okay. So this voltage is 4 volts. And therefore the D here would be simply 2 over 4 equals 0.5. Okay. So what we have achieved is we have made the duty ratio significantly larger from 0.1 to 0.01 to 0.5, and therefore the requirement of L is much smaller, as we can infer from the equation that we saw in the previous slide. Next, let's look at the input current IN. Now, to draw this, I'm going to ignore the ripple in the inductor current. Ripple current is neglected, or is approximately 0. Therefore, if we had to draw the inductor current waveform, this would be a flat 10 amperes current. Yes, this is IL. So under this assumption, if I were to draw the input current, it would look something like this. When the switch is on, the current is same as the load current, 10 amperes, and when the switch is off, the current is 0. Okay. And the average of this is given by this dotted line. I can get this by taking the average of this entire IN, or I could use power balance as done here. Okay. So the input power, same as the output power, is 2 volts times 10 amperes, that is 20 watts, divided by an input voltage of 200 volts. That gives you the 0.1 amperes average input current. Now, if I use the same transformer which I used to get this this new waveform, so that was a transformer which had 50 turns on the primary and 1 turn on the secondary. So this is 50:1. Now that we had learned about dot polarities, it is going to be like this. Okay. So this transformer not only reduces the voltage on the primary side from 200 volts to 4 volts as we saw here, but it also transforms the current seen on the secondary side. It reduces it by the same factor of 50 as seen from the primary side. So the current would have the waveform as shown in this plot. When the switch is on, the current would be, instead of 10 amperes, would be N times 10. So N is 1 over 50, so this would be 10 over 50 is the magnitude of the current at this instant, and it would be 0 when the switch is off from the input side. Okay. And the average of this should be exactly equal to the previous case, 0.1 amperes, and that is what we see here as well. Okay. But this was achieved by having a smaller peak value and increased on interval. The D is was 0.5 in this case, right, and D was 0.01 here. Okay. Same average input current. Okay, and notice that the input current IN is same as the switch current as well. Okay. So therefore, this would be the switch current waveform, and you can clearly see that we have already solved the two major disadvantages of the non-isolated version. The first one was the total switch VA rating. So the switch now handles only a peak current of 10 over 50, 1/50th of the original case. So that reduces the total VA rating of the switch. And the second one was the switching losses, and it is for the same reason. During the switching transition, the voltage may still be 200 volts. It depends on the type of isolated version that we use. It can actually be more than 200 volts, but the current comes down by a factor of 50. Therefore, the switching losses would also reduce significantly. Okay. So we see that all the three issues that we saw with the original case, they have been addressed by introducing the transformer. Now the question is, what should be the correct topology, correct circuit configuration that introduces this transformer, but also does not violate any of the principles needed, any of the requirements of isolated converters, namely the flex continuity, the volt-second balance. So starting from this buck converter, our objective is to introduce a transformer such that the voltage across the diode, this voltage is instead of switching between 200 and 0, it needs to switch between 4 and 0, right? So we could think of putting a transformer right at this point, right, as shown here. Okay. So the idea would be, this voltage is 200 volts, this is a turns ratio of 50:1, and the voltage that I get here is 4 volts, and then I switch that to get the required waveform. Okay. But this is a very trivial attempt. Okay, we can clearly see that we cannot, just by looking at this section, we cannot apply a DC voltage to any of the transformer winding, so that we are violating that, and therefore this is not a valid circuit. Okay, it's not valid, and the reason why it is not valid is it violates the volt-second balance for a transformer. So volt-second balance would be the primary voltage V primary, its average should be equal to 0, and that is being violated. It is not equal to 0 in this case. Okay, so we saw that going from this buck converter to this version by putting a transformer here is not a valid circuit because we ended up applying the full DC voltage across the primary. Okay, so let me try to remove that problem by shifting this this MOSFET to the primary side, the switch to the primary side, such that we no longer directly connect the primary winding to the DC source, and that situation is shown here. Okay, so is this a valid circuit? The idea is when you switch on, turn on the MOSFET, this voltage will be 200 volts, and this is still a 50 to 1 turns ratio. So when this is 200 volts, this would be 4 volts. Okay, and so is this a valid circuit? If you look at the flex continuity principle, when the switch was conducting and when it was just turned off, the current was entering the dot on the primary side, and for flex continuity, we require a current that continues to enter a dot in some other winding, and in the secondary side we see that this diode has the correct direction to force a current into the dot. Therefore the flex continuity from that point of view, it is okay. But is this a valid circuit? Think about it. It is still not a valid circuit. The reason is it violates the volt-second balance principle. Again, it violates the volt-second balance required for a transformer. I may have mentioned this before. Anytime you see a diode connected directly across a transformer winding, as in this case, it is most likely an invalid circuit. Okay. The reason is because of the diode, the voltage on that winding can be positive but not negative. The diode would short out the negative polarity. Okay. Same thing, so the same voltage would be seen on the primary, just scaled by the turns ratio. So the V primary or V secondary, either of the two, its average cannot be 0. It is not equal to 0. Okay. Therefore, it violates the volt-second balance principle. Okay. So once again, it is not a valid circuit, but we are getting close. Okay, so then we see that it is this diode directly across the secondary which is causing a problem. It violates the volt-second balance. So let's and this diode is really needed to have freewheeling for this inductor current. The inductor current needs a path when the switch is off. Okay, so we cannot eliminate this. So let's prevent this short circuiting of the winding by the diode during the off interval by putting a diode at this point. So that is shown in this new schematic. All I've done differently is I've added this diode here, and that makes this winding not directly in parallel across this diode. Okay. So is this a valid circuit? Okay. It is still not a valid circuit because by introducing this diode here, I have violated the flex continuity principle. Recall that just in the previous slide I mentioned the previous circuit, like this circuit was okay from a flex continuity point of view because at the turn off instant current was entering the dot. I required a current to enter the dot on the secondary side once the switch is turned off. Now in the absence of this diode it was possible, but the moment I introduce this diode, I call this as D1. The moment I introduce D1, the flex continuity is violated because there is no path for a current that supports a flex in the core. So this circuit is invalid because it violates the flex continuity principle. Okay, so the last circuit, so this is the same as the one that I showed in the previous slide, the very last one. It is getting very close to being the final circuit, the final isolated version. We just have to ensure that we provide a mechanism for maintaining the flex continuity. Okay. So as long as we can ensure that, and also we have to make sure that in doing so, we do not end up violating the volt-second balance principles. Both of them have to be simultaneously met. And there are several schemes that satisfy both of these requirements. And we're going to look at a few of them in the next few slides. Okay, so this is the last version which we saw was invalid because it violated the flex continuity. So we are going to attempt to provide a mechanism for maintaining the flex continuity. Okay. So the two schemes that I'm going to show in this slide, they are valid topologies, but they are dissipative, meaning they waste the stored energy, the magnetizing inductance, each time the converter undergoes a switching. Okay. Okay, the flex, so first of all, notice that the circuit drawn here, this is identical to the one at the top, identical. These two are identical. Okay? Especially if you look at the secondary side, it is exactly the same on both the figures. Okay? On the primary side also, I will say they are identical, except that here it is redrawn in a slightly different way. Just the switch here is drawn at the bottom, and that does not change the circuit in any way. This is how normally the isolated version is drawn, and that's why I'm drawing it this way. Okay? Now the circuit as drawn is identical to the first case, and in order to maintain flux continuity, what I do is I add this extra circuit. Okay, this just like a snubber circuit, and just provides a path for the magnetizing current to continue to flow. Once the switch is turned off, the current that was flowing in this direction would flow through the diode and go into the capacitor, and eventually during the next period, the capacitor would discharge the newly stored energy into the resistance. Okay, so it provides a path for the current to maintain the flux continuity. But as you can see, the energy stored in the magnetizing inductance is actually dissipated in this resistance. Okay? So it's a valid circuit, but it's not a preferred circuit because it will be very inefficient. Okay? Another circuit where which is also another dissipative circuit but a valid circuit, is to use a Zener diode as shown here. Okay. So now when the switch is turned off, the magnetizing current would flow through the diode and into the Zener, and it dissipates the stored energy in the Zener. Okay. So the magnetizing current times the voltage of the Zener is the power dissipated. So in both the circuits, the energy stored in the magnetizing inductance is actually dissipated in the resistance in the first case and in the Zener diode in the second case. And we can also verify that in the case of the first circuit, when the diode conducts, we apply this capacitor voltage, which is actually positive on the lower end, positive on the lower end, negative at the top. So we apply really a negative voltage across the winding. And in the second circuit also, when this diode is conducting, it is a Zener voltage applied as a negative voltage across the winding, and therefore we are not violating the volt-second balance by applying both positive and negative voltages in a given switching period. Okay, so that brings us to our final preferred solutions, namely the forward converter. Okay. So the circuit schematic shown here, which is actually coming from this circuit, and we just make a small change to provide flux continuity, and so this is called as the forward converter, which we'll be studying in several future videos. So the main difference, the only difference between this circuit and the new circuit is what is shown in this red dotted box, and that is it's called as the reset windings. We add an extra winding to the transformer, a very small winding, and it's connected through the diode to the input source. Okay? So the basic operating principle is here. The mechanism of flux continuity. When the primary side switch is turned off, the magnetizing current, which was responsible for the flux, was entering the dot. Okay? So all we need is a current in any other winding that enters the dot. In the secondary side, that is not possible because of this diode. Whereas here this is called as the reset winding, the diode is connected with the correct polarity to support a current that enters the dot at this point. Okay? So the moment the primary side MOSFET is turned off, the stored energy in the core would force the diode, I'll call this as D reset. It will force the D reset to forward bias, force it to conduct, and the flux continuity is maintained by having a current entering the dot in the reset winding. And this way, the stored energy is actually being fed back into the source instead of being dissipated in a Zener or in a resistance. So that's the advantage. It's both a valid as well as a very efficient topology, and the energy in the magnetizing inductance is actually fed back to the source. Another variation would be to have the third winding shown here, instead of being connected to the input source, can be connected to the load directly here. Okay. So once again, when the MOSFET is turned off, we need a current that enters the dot, and this diode is placed such that it can support a current that goes this way and enters the dot here. Okay. So that will maintain the flux continuity, and in this case the energy stored in the magnetizing inductance is actually fed to the load directly. And we can also verify that whenever the extra winding, the reset winding here or here, whenever that winding conducts, the voltage is really negative. The voltage of the dot with respect to the undotted end is negative. Therefore, the volt second balance can be maintained. The average voltage can be zero because we have both positive and negative intervals. Then we also have several two-switch versions of the forward converter. So this is a two-switch forward converter, and there is another widely popular topology at present called the active reset or active clamped forward converter, again using two switches, and this results in zero voltage switching, ZVS, and therefore it is becoming popular. Okay. And we will certainly be looking at these also in future videos, but the focus of the next several videos would be on this forward converter with this reset winding providing the flux continuity mechanism.